I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of December 2023. The question is from the section Complex Analysis and it is related to the concept of real differentiable function in complex analysis. This question is placed in part B, which is a multiple choice question. It carries 3 marks. The question ID is 704035. Right. The given question is, let f from C to C be a real differentiable function. Read carefully. It is a real differentiable function. Define u and v are functions or real valued functions defined on R square by u of x comma y is the real part of f of x plus iy and v of x comma y is the imaginary part of f of x plus iy, where x and y are real numbers. Let grad u or nebula u is equal to the ordered pair ux comma uy denote the gradient. So the grad u is the ordered pair ux comma uy. Which one of the following is necessarily true? We are given 4 options. Option 1, for C1, C2 belongs to the set of complex numbers. The level curves u is equal to C1 and v is equal to C2 are orthogonal wherever they intersect. Option 2, grad u dot grad v is equal to 0 at every point. Option 3, if f is an entire function, then grad u dot grad v is equal to 0 at every point. Option 4, if grad u dot grad v is 0 at every point, then f is an entire function. Right. Before entering into the discussion of the questions, the options, first let us familiarize this concept of real differentiable function. We have functions of complex variables and we know differentiability of the complex function. The differentiability of the complex function, what we mean is complex differentiable function. There. So there is another concept which is here, that is real differentiable function. Normally we do not find this definition in our textbooks. I am sure that we don't teach at our MSc this concept. But this is not a difficult concept. It is a very simple definition. A complex function f of x plus iy is equal to u of x comma y plus I v of x comma y is real differentiable at a comma b. When this function is called a real differentiable function at a comma b, if the real valued functions uxy, u of x comma y and v of x comma y, which are functions of 2 variables, are differentiable at the point AB in the sense of real analysis, that is, as we have defined in the functions of two variables. So, a complex function f of x plus iy is equal to u of x comma y plus iv of x comma y is said to be a real differentiable function at the point a comma b if this real and imaginary parts, which are real valued functions of two variables, are differentiable at that point a b as functions of two variables. These are differentiable functions as functions of two variables. Right. So, here we write down a sufficient condition for real differentiability. If the partial derivatives of u and v with respect to x and y exist, that is ux, uy, vx, vy exists and are continuous, and these four first order partial derivatives are continuous at a comma b, then uxy and vxy are differentiable, and thereby f of x plus iy is equal to uxy plus ivxy is a real differentiable at that point. So, conditions are the partial derivatives of u and v with respect to x and y exist and they are continuous at a comma b, then these uxy and vxy are differentiable at that point a comma b, and thereby this function f of x plus iy is equal to uxy plus ivxy is a real differentiable at this point ab. Right. Here we give two examples. Example, the function f of z is equal to z bar is a real differentiable everywhere. Second example, the function f of z is equal to x plus y plus I times 2x plus y is a real differentiable everywhere. These are the two examples what we are giving here because we are using these in the course of the discussion of the problem. Right. Now, let's now get into the question. So, we discussed the solution of the given question. Given f c to c is a real differentiable function, we know what is a real differentiable function, where f of x plus iy is uxy plus ivxy. Given grad u is ux comma uy is the gradient. Right. Let's call on option 3. If f is an entire function, then grad u dot grad v is equal to 0 at every point. Mind you, f is an entire function. F is not real differentiable function. It is an entire function. F of z is equal to u plus iv is an entire function. What's the meaning of that? It is analytic everywhere in the complex plane. Right. And it is analytic at every point of C, then Cauchy-Riemann equations are satisfied. That is ux is equal to vy and uy is equal to minus vx at every point of R square. These are the Cauchy-Riemann equations. Right. Now, del u dot del v. Del u is ux comma uy ordered pair dot del v is vx comma vy. Take the dot product ux vx plus uy vy. Right. Now, this is equal to ux. For ux, we have written vy vx plus uy, we have written minus vx vy. So, they cancel and we get 0, and we have used the Cauchy-Riemann equations there. Thus, del u dot del v is 0 at every point. Thus, when f is an entire function, grad u dot grad v is 0 at every point. Yes, this is true. So, thus, option 3 is true. Right. We move on to option 4. If the converse of 3 we are asking. If del u dot del v is 0 at every point, then will the function f be an entire function? Not necessarily. If you say not necessarily, you have to give a counter example where this fails. Consider f of z is equal to z bar. Z bar is x minus iy. U is x, v is minus y. Remember, this function f of z is equal to z bar is a real differentiable function. And you take ux is 1, uy is 0, vx is 0, vy is minus 1. Now, del u dot del v is ux comma uy, ux comma uy, ux is 1 comma 0 dot uy, vx comma vy, vx comma vy 0 comma minus 1. Take the dot product, that is 1 into 0 plus 0 into minus 1 is 0. But f of z is equal to z bar is nowhere analytic. It is a standard result, It is analytic nowhere. F of z is equal to z bar is nowhere analytic. Del u dot del v is 0 doesn't mean that f is an entire function. Here is an example, f of z is equal to z bar, which is nowhere analytic, for which del u dot del v is 0. So, thus the statement given in option 4 is not necessarily true. Therefore, option 4 is not true. Remember, real differentiable functions which are not complex differentiable, stand as the counterexamples here. We move on to the next option. Option 1. For C1, C2 belongs to C, the level curves u is equal to C1, v is equal to C2 are orthogonal wherever they intersect. We have f of x plus iy is uxy plus ivxy. If we equate uxy is equal to C1, vxy is equal to C2, then we get the level curves. If f is an analytic function, these level curves uxy is equal to C1, vxy is equal to C2 are orthogonal. But if we take f to be a real differentiable function, because nothing is given, therefore we have to take f is a real differentiable function. For that, u is equal to C1, v is equal to C2, the level curves, will they be orthogonal wherever they intersect? That's the question. Right. So we have the level curves uxy is equal to C1, vxy is equal to C2. What is uxy? Uxy is the real part of f of x plus iy. What is f? F is a real differentiable function. So now take uxy is equal to C1. Differentiate with respect to x. Then ux plus uy dy by dx. Dy by dx, we keep it as m1. m1 is equal to minus ux by uy. In a similar fashion, vxy is equal to C2 will give you m2 is equal to minus vx by vy. Now, u is equal to C1, v is equal to C2 are orthogonal wherever they intersect will imply m1, m2 is equal to minus 1 at the point of intersection. What is m1? Minus ux by uy multiplied by m2 minus vx by vy is equal to minus 1. Right. Now, simplifying, you will get ux vx plus uy vy is equal to 0. That is, this is precisely del u dot del v is equal to 0 at the point of intersection. Now, consider an example like this. That means del u dot del v is 0 at the point of intersection. Consider this example. Uxy is equal to x plus y is equal to c1 and vxy is equal to 2x plus y is equal to c2. They are intersecting curves. uxy is equal to c1, vxy is equal to c2. They intersect. Right. And what are these? These are the real and imaginary parts of a real differentiable function. Remember here, f of x plus iy for this u, that is x plus y plus I, for this v, 2x plus y is a real differentiable function. Now, del u dot del v is equal to ux comma uy dot vx comma vy. What is ux? 1. Uy? 1. Vx? 2. Vy? 1. So multiply, that is equal to 1 comma 1 dot 2 comma 1. Then taking the dot product, 1 into 2 plus 1 into 1 not equal to 0 at the point of intersection. Is not equal to 0 at the point of intersection. So that means they are not orthogonal. So thus option 1 is not necessarily true. So the option 1 says are orthogonal wherever they intersect, but they are not orthogonal. The condition is not satisfied. The condition is not satisfied at the point of intersection. Orthogonality condition is not satisfied. Therefore, is not necessarily true. They are not orthogonal wherever they intersect. Not necessary. Not necessary. Now, let's move to the option 2. Del u dot del v is equal to 0 at every point. But just now we have seen, for this above example, just now we have seen del u dot del v is not 0. But this option says it is equal to 0 at every point. So, this is not necessarily true. We have seen in the above example, del u dot del v is not 0 at the point of intersection. Therefore, option 2 is not true. So, summarizing all the options, the answer to this question is option 3. That is the detailed discussion of the solution of the given question from the complex analysis, which is related to the concept of real differentiable function in complex analysis. And in my opinion, this question is difficult in the examination. Many of the students, they do not know. Why many of the students, we don't teach this concept called a real differentiable function in complex analysis. Therefore, this question, people, will look at them as if that they don't know this one. So, in my opinion, not many people might not have answered this question. Anyway, that is the concept, and that's how this question can be answered. I am sure that you understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. I wish you all the best. Thank you.